First of all, I will not be using a microphone. Can you hear me? Good. Do you need a microphone for recording, or you do not? Or you do? So this, having it there, is that good enough? Good. That's wonderful. How many of you speak perfect English? Okay. That's all right. That's all right. I did not expect that everybody would speak perfect English, so I would try in my speaking to use more simple words so that everybody would understand. And this is going to be a lecture, not a seminar. So if you have any questions at any time, raise your hand and ask your question. We try to answer that. Then if I find out that it would take a lot more time to answer a particular question, then I would politely ask to discuss it after the material. But the only stupid question that is asked is the question that it is not asked. If you have anything that you do not understand, please immediately ask, because it's very important to go forward. Another question that I have for you: how many of you have seen a presentation of mine before? Have you, any of you, seen a presentation given by me? Good. So then in that case, I only have to apologize to Professor Kotana and some of my colleagues, because there are some duplicate slides from my previous presentation. But since you are new in this field, for most of you it is new. So with that, the topic of my presentation is not historical. It's looking at the advances in heat island countermeasure technologies. So with that, I always would like to bring in a prospectus toward any given lecture. And I am reviewing today's history in science. And starting from 1945, today is the day that the United Nations was founded in San Francisco. Then in 1949, it was moved to New York City. In 1836, you all look at the match, you just make a friction and the light would come in. But you know that the fire has been the biggest invention of the human being. And finally, in 1836, a patent was given for a new match. So what you see is million years of history behind it that is so simple. That is the heart of the science. Once you understand everything that's so simple that you can explain it to a 5-year-old, then that is science. In 1851, two of the satellites of Uranus was discovered, and they were named after Ariel and Umbriel. Do you know what is the origin of these names? They are coming from Shakespearean actors, Ariel and Umbriel. In 1861, the first intercontinental telegram was invented. Now, each one of you have a phone like this, and you think that's the way the world was. But humanity has to work very, very hard in order to get to a simple telegram from one part of the world to the other. In 1876, a U.S. patent was issued for an alarm clock. Wake me up at 7 o'clock. Now you go right on your cell phone, click a button, and an alarm clock comes in, you set the time. Things change, and they change very fast. And finally, today is the day that the last Concorde flight in 2003 flew. and after that, Concord stopped existing. Having said all of that, to me the most important factor is the last item. Today, like any other day, is a day that millions of people have died and born, and nobody knows about it. As engineers, it is our responsibility to be worried about these people. History is the life of these people. This is not history. These are only some highlights of the history. So, therefore, everything that we are doing as environmentalists, we are trying to improve our life a little bit better. Many of us are never going to be recognized. That's fine. We are part of millions of people. Okay? So, with that, I'm going to now jumping into the science. There is a terminology known as urban heat island. A heat island is being given to the cities because downtown area are warmer than suburban areas. You all know that during the summer, most people would go on vacation in a rural area because it's typically in the mountain, a better climate. So, urban heat islands, which are typically higher temperatures, would have consequences that as the temperature increases, the demand for air conditioning in commercial buildings and some of the new residential buildings increases. As an example, in Southern California, in the Department of Los Angeles Department of Water and Power, the demand for electricity increases from 10 gigawatt to about 16 gigawatt as an interval of 10 degrees higher in temperature. So man-made has created a condition to require air conditioning. These air conditionings cost money and environmental health, cost global warming, and there are ways that we can avoid some of that. As an example, if you look at also in Tokyo area, for every degree higher urban temperature, you need to have an additional 5 gigawatt of power. A gigawatt of power is 1 billion watt. Each gigawatt of power costs around $2 billion. So each degree Celsius increase in temperature costs an investment of $10 billion. It's a lot of money. In addition to that, also as the temperature increases, the air quality decreases. The plot on the lower right hand shows the concentration of smog ozone, and as you see, when the temperature is around 25, the concentration of the ozones is below the California standard requirement. But once the temperature increases from 25 to 35, basically all the days become smoggy. So now we are talking about a heat island that it is man-made effect, causes additional energy use, causes urban air quality, and if buildings are not conditioned, it also causes health issue and comfort issue for the citizens. So what is a heat island? Looking at an aerial photo of most metropolitan area, you see two dominant surfaces: roofs, pavements. Roofs, pavements. What is a roof? It's a man-made factor. What is a pavement? It's a man-made structure. So we can do these things properly because we are doing it and we have to maintain it every so often. If we do it correctly, it would improve our environmental condition. And by the way, this is the case basically everywhere you go around the world. Now, here is another factor. This is August 2003. A heat storm came in Europe. Some of you may not be old enough to remember that. But Italy and France were the major victim of this heat wave. Over 50,000 people had an early death. You know, everybody is born one day, they die another day. There is, statistics is perfect, there is no question on that. But they died prematurely. The time was not there to them for die. They died because of the heat storm. Now, the value of human life matters. That matters whether that person is living in Europe or living in Africa. So improving the condition of the living of the humans is very important to us. So here is what the processes works. If you have a solution for the heat island mitigation are typically cooler roofs and urban vegetation. A cooler roof would reduce air conditioning energy use. Lower air conditioning would require less power. Less power would require less fuel to be burned. Less fuel to be burned, less emissions. So air quality would be better. Now, if in a city or a neighborhood you have plenty of cool roofs, plenty of vegetation, plenty of cool pavements, the entire community is going to be cooler. So if your house happens to be in a cooler community, it would require less air conditioning. On top of that, if you have a lower ambient temperature, the data show, as I showed in one of them, the air quality can improve significantly. And finally, this is something that we have we started to work as of a decade ago, that if you increase the reflectivity of the surface area anywhere in the world, that would reflect the short wave radiation from the sun back to space. And that would lead into cooling the globe. We are calling this phenomena of the material in this radiation range. Anything above this radiation range, eyes are not sensitive to it. But surfaces absorb it as a heat. So you can define any color that you want to be characteristics of the visible color that you want in here, but make them 100% reflective in the near infrared. As an example, if you want to have a jet black surface with a reflectivity of 0 in the visible, so you would develop a material that has a reflectivity 0 in here, 100% there. On the average, that jet black surface has a reflectivity of 50%. So is that such a thing possible? The answer is yes. Here is an example of a brown standard and a brown, cool brown that are designed to be cool. If you look at the spectral reflectance on the lower right-hand side, you would find out in the visible they are identical. Then in the near infrared, you would find out that the cool brown has a reflectivity increasing all the way to 70%, while a standard brown has a reflectivity around 10%. So if you put these in the summer, on the hottest summer day, this surface is 10 degrees cooler than that. And if you ask people which one is what, without touching it, they would not be able to learn about it. Actually, there is a true story about this. I was demonstrating some of this in the U.S. House of Congress. I had a booth demonstrating some of these cool materials, and I had an infrared sensor that would target this and show the temperature. The battery of my infrared sensor died, and I didn't have time to go and get a new battery, and I was not well prepared to have a spare battery. So many of House of Representative members that they came, the only way for them to understand whether this is cool or hot was to touch that. When they touched that, some of them burned their hand. So it is calling a burning impression. So they still, some of the House of Representatives who are supporters of the technology use that terminology. You're looking for the, yes. Thank you. Wonderful. So now let us go. This one? How does it go?
No.
Okay, good. So, good. Now here is another technology. Remember that I was talking about the cool black? Here are 4 blacks being measured and developed at the laboratory. As you see, they are all black. One of the characteristics of the material is that not everything happens on the first layer of atomic structure of the material. When the light comes in and is incident on the first layer, it has 3 options. First option, to be absorbed. Second option, to be reflected. Third option, nothing happened to it, go to the next layer. The same thing happens, absorbed, reflected, or nothing happens to it. So an engineering technology who would build materials that offer the choice of the color, but offer reflectance on the background is a technology that has been evolved within the last 20 years. So this particular black agent is dioxazine purple. It is being applied on a metallic background. This one is being applied the same material on a thick white background. The third one is a thin white background. And the fourth one is on a black background. And again, as long as the eyes is concerned, they are exactly the same. Now look at their spectral properties. Eyes say that they are exactly the same. But when you look at the properties in the near infrared, you would find out that the materials on the metallic and white background have a much higher reflectivity, almost to 90%. So when you integrate it all, you would find out that the jet black standard has a reflectivity of 5%, but the reflectivity of engineering material is about over 40%. Remember that a few minutes ago, I said that you can develop a jet black material that has a reflectivity of about 50%. You are already 80% over there with some simple ingenuity. So the question is that, okay, doing things at the lab is good. It brings a level of satisfaction, but you would get a lot more level of satisfaction if you see the products in the market. So from the very beginning, in my group, both at Lawrence Berkeley Lab and at Concordia, I have been working directly with the industrial partners. So our technology was integrated with their technology. We had a little bit of technical an academic background. They had a lot of application background. Together, we would perfect fit, and products come to the market. So here is an example of standard coatings versus cool colored coatings. A lot of concrete tiles over time, their change. Oh, thank you. That makes a big difference. By the way, a copy of this presentation is available to whoever would like to have it. I have already left a copy to Anna Laura, but if you also would like to send an email to me and get it directly from me, so you would be on my favorite list, I would be more than happy to oblige. So, cool colored materials versus standard coatings. Cool colored tiles approaching a reflectivity of about 75%. Cool colored metal roofings approaching a reflectivity very, very high. And also fiberglass asphalt shingle, cool colored. These products are available in the market. Now, newer products are being developed at the lab, and one of those products is what we call it latent heat cool white. Basically, this is a sponge rock-like roofing that it works very well when there is high pouring of rain in a short time. So flood is a major issue. So in the old days, when the land was not engineered, this water would be absorbed by the ground. But in a development, the water from the pavements, from the roofs, run into the city, and if the rain storm is very severe, it would cause flood. So this particular material has the capability of absorbing this water, and as the result of that would reduce or regulate the flow of the water from the roof. But once the water is absorbed on the roof, it would keep the roof cool for few more days. So this type of products are very useful for tropical range. And here is this product when it is dry. When it becomes wet, this is the thickness of the product. This is the amount of the water that it is absorbed on its roof. Of course, you got to make sure that the structure can hold that additional weight of the water. Otherwise, you are trying to solve the water problem, the entire roof would collapse. So it is an integrated problem. Another technology that it is again very simple is when you want to have the choice of color and you do not want to invest a lot of material, another class of material that it is coming, we are calling it directional reflectivity. This is not retroreflective. It is directional reflective. Consider a roof, a slope roof. People would like to see the color of the choice when they are walking on the streets. But the sun is up there and would see the roof in a different way. So if I see the color that I want, but the sun sees white, I have achieved my objective. So here is the way that this material has been engineered. This is an example of that. This material looking from the ground, this material looked by the sun. The reflectivity in this direction is 60%. The reflectivity in this direction is 20%. So how do you do that? For a granulated surface, you brush the surface in one direction in the color of the choice that you want, or white color. You get your answer immediately, almost at no cost. So there are ways to engineer this material, not necessarily very expensively. And of course, retroreflective, which particularly lend themselves to the environment which has heavy urban setting. When the radiation of the sun is incident on the wall, you do not want that radiation to be reflected through the window of another person. So it would reflect the radiation in the direction that it comes. And again, in most cases, these materials can be developed by putting hollow spheres into the coating on the top layer that would reflect the radiation after 3 bounces in the direction that it is coming. These retroreflective materials are the same when you are driving at night on the freeways, on the autobahns. Their light would come in the direction of the light of your car. This is one of the fascinating topics that we have been testing, and the material exists over thousands of years. But the properties of it have been investigated only within the last 5 years. So this is an example of material which is called fluorescent pigment. A fluorescent pigment is a material that would absorb light in one wavelength and emit light in another wavelength. So a lot of you have seen these older watches that glow at dark because they absorb a lot of light during the day, and then during the night they would glow a little bit light, so you would be able to see what time it is. So this is the same technology. So this particular one is a ruby red material that it is being tested. These materials that are not the fluorescent, a standard reflectance of them is about 20%. Now, if you make them cool, their reflectance increases from 20% to 40%. Now, if you make them fluorescent, some of the light that it is absorbed in the visible range would be emitted in the near infrared range at over 60% reflectance. Now, here is the nice thing about this. Some of these materials have been discovered in tombs of pharaohs in Egypt with an age of 5,000 years. And still they perform. So you have material that it is being used 5,000 years ago. It still has that capability after 5,000. So there is no question whether it is durable or not. And it is not being used right now. So having our eyes open and looking how we can help our community by knowing what it is the most important factor of our mission as engineers. Now, when you start something, before you know it, you can see that you can apply your knowledge into an adjacent environment. As an example, a lot of surfaces that we have, you do not have to go a long way. Just look around the buildings in here. They get dark or black over time. Windows would collect dust. The question here is that how I can make the deposition of the particulate matters on the surfaces to a minimum level. This is called a class of self-cleaning material, and it is applied on the roof. It is applied in an interior shade. It is applied on a wall, and it is applied on a car on one side. This car had been in operation for about 5 years, and you see the difference. This was the original color that was coated with titanium dioxide in anodized ways, and then this is the part that it is not covered. And the picture tells the entire history. Now, does this save energy? I don't know, but let us look at this thing. In most high-rise buildings, the windows have to be cleaned every 3 to 6 months. It costs typically in the order of $20 per square meter to clean those windows. Now, do the calculations. If you apply a white coating on the windows, self-cleaning coatings on those windows, these are totally transparent, the interval of the cleaning would go down to once every 2 or 3 years. So you would save every 3 years 5 times 20, $100 per square meter of the window cleaning. So take your building, find out how much window you have, and then you would find out how huge number it is. Energy component of it is another factor, which is actually a very, very small amount. So here is another application of this material, which is being produced or tested by Tutu in Japan. By the way, Japanese are really leading the application of titanium dioxide in the world. And Class A materials are all those tiles that are treated with titanium dioxide. Class B materials are not treated at all. Again, it tells the story by itself. Now, the roof typically in an urban setting makes about 25% of the surface area. Pavements in a typical new city make about 40% of the urban area. So addressing the urban heat islands without mentioning pavements, you have not really achieved the fullest potential. So the pavements and understanding how to implement those cool pavement technologies is very important. Even though the pavements in most cases are very simple material, it would be very difficult to implement cool pavements because of different ownership and different application. So pavements are used in parking lots, alleys, driveway, bridges, plazas, playground, streets, sidewalks, runways. There are different materials, and each of these are being owned by different group of people. And they are being monitored by different level of technologies. So trying to devise a system that would allow the pavement industry to be your partners is highly critical. Note that this is a very important factor. About 85% of the pavements of the world are made from asphalt. Asphalt is residual of the refining process. So if the refining industry is not allowed to dump their asphalt on the streets, the cost of the gasoline would be about $50 a liter, 50 euros a liter, because they have to treat this waste somehow. Remember that the nuclear energy, the biggest problem of nuclear energy, in addition to its safety issue, is the waste treatment, how to manage the waste. Now, asphalt industry has found a way to dump their waste in your backyard and charge you for it. That's ingenuity that they have been able to do that. And of course, we all know that over time, the asphalt usage is going to go down because our resources for petroleum are limited, and it's only a matter of time when we are going to do that. But the point here that I'm mentioning is trying to address all these different materials with different ownership while the asphalt industry is fighting against you. It's not very easy. You have to be working with them. Here is an example of visual measurements of a visual observation of a sample of a green area with the asphalt layer and an infrared image. And as you see, the asphalt surfaces are much, much hotter. When the surface is hotter, the air that brushes on that also becomes hot. As a result of that, the urban heat island intensity increases. Now, this particular slide shows a sample of existing technologies that one can use in order to replace the coolant backdrop surfaces. These technologies, they are already being used. One of them is called chip seal technology. In an asphalt, what you would do is that you would mix aggregates with the asphalt. This is called hot mix. Then you spread them on the ground. Then you would roll them in and let it cool down. So that's one. The other technology is that, which is called the chip seal technology, is made out of 2 trucks and a roller. First truck sprays asphalt on the ground. The second truck sprays granule on the ground. The third truck, or the roller, would press these granules or aggregates into the asphalt. And there is a vacuum at the end of this that vacuums all the loose asphalt, loose granules. This technology has been used in the low traffic environment very, very efficiently within the last 30 to 40 years. Another technology that it is being used are development of the coatings. This is a driveway that most of the time is used in the warehouses, that the truck comes in and loads cargo on it. Now, over time, this becomes dirty because of all the leakage of the oil from the trucks. So they resurface it every now and then. There are products already available for this resurfacing with reflectivity as much as 50%. This has a reflectivity of 50% at a very, very minimal incremental cost, and in most cases, no incremental cost at all. In areas that you have substantial amount of rain, rather than having solid layer of asphalt, you would have something which is known as grasscrete. So these are lattices of concrete that you let grass to grow on them. These technologies are being used throughout the world in urban areas. Japan, Singapore, I have seen also some in Italy here and there. Then also there is the porous asphalt that is designed in order to manage the flood in the cities. Now, here is the interesting thing about asphalt, the information that it is coming gradually. There have been a study done looking at the lighting level, intensity of the lighting, and hence the observation of the pedestrian on these asphalt. One of them is being in dark color, then the other in the light pavement. They have found out in order to achieve the same level of luminance in the environment, they can have 27 fixtures per mile rather than 39 fixtures per mile. So you have exactly the same level of observation, but with 12 out of 39 or 12 out of 40, 30% less lighting. The source is Stark, 1986, as old as that. Now here is the same pavement measured under the same lighting after it is being coated in the light color asphalt. If you are a pedestrian, which one you think you would be feeling more safe to walk on this? This one or this one? Obviously, if you are walking on this, there is a higher chance that you would be having an accident with an incoming car. In here, you would be a lot more visible. So that issue also have to be integrated into the design and use of the asphalt. Tunnels. All the tunnels are artificially laid. And in the United States, most tunnels that you would go through as of 50, 60 years ago, they are in light color. Unfortunately, I do not know how and why the roof is not light colored. But all their walls and the paved surfaces in lighter color. I have seen many tunnels around here and the rest of Europe that are not following this simple approach. So more lights in a dark environment versus less light with the same illumination in the same environment. And finally, in terms of the asphalt, is the performance of them in the streets. Here is a test that it is being done in the lab to measure the performance of the asphalt. The test is called rotting test. The rotting test simulates a bus stop. What would happen in a bus stop is that there is pavement, bus comes in, stops. With the stopping, it pushes the pavement forward. Then, after it has loaded their customers, it would start moving. So it pulls forward again. So now this experiment, our rotting test is exactly like that. You have sample in the lab, and then you have a tire comes in and it stops. Then you measure the number of these revolutions, repetitions, until the time that cracks are starting to develop on your asphalt. When the width of the crack is about 1/4 of the inch, they call it the asphalt has failed. That's the standard that they have developed. Now, same asphalt, one of them at 50 degrees Celsius, the other at 42 degrees Celsius, have been tested. The one that it is at 53 degrees Celsius has failed after about 18,000 repetition of the test. The other one, the white one, with the temperature difference of only about 10 degrees Celsius, has been performing up to about 250,000 repetition without being failed. So here is how important is temperature in the design of the proper asphalt. Now, this is not the only reason that the asphalt fails, but shows at least in one or two tests like this, temperature plays a very, very important factor. There is a temperature on the surface and also the temperature variation throughout the 24 hours. Having a light color asphalt would reduce the surface temperature and also reduce the temperature variation. So it would reduce the expansion and contraction that the asphalt would have throughout the day. So the basic technologies has to be made in the form that it is understandable by the decision makers in order to justify that technology. So the ways that you would do, you would basically try to translate this thing in terms of energy and peak demand savings, in terms of the material performance, such as rather than changing your roof every 10 years, you would change your roofs every 15 years. That is something that I understand very well as a consumer. In terms of the micro and microclimate and the comfort that it involves associated with that. So a lot of work has been going on, and my colleagues in Italy, France, Greece, Japan, Singapore, India, South Africa, Mexico, Brazil, they are all around the world. They are pushing this technology as it is applicable in their own communities. Here is an example of a test that we did. This is very important to the policymakers, that you take a regular cap sheet roof, you monitor its performance, then you put a coating on that, continue monitoring. Then this slide shows when we have half-coated the surface of this. As you see, the coated part is very cool. The uncoated part is hot. The seams that are black is the hottest. And now, when you measure the performance of this air conditioning performance of the same building during before and after, the weather also changes. So you have to normalize the condition for the condition either before and post to compare those. When you do that, you would find out that for a typical single-story building, you would save anywhere between 10 to 20% of air conditioning energy use. People immediately understand and absorb that. A 10% is typically in the order of about $1 per square meter per year. A roof lasting for 20 years, that's $20 per square meter per year. Typically, that's about the cost of the roof itself. So people understand that. When such a thing happens, such information is becoming available, then the rule-making industries such as California Title 24, the European Energy Conservation Code, the International Energy Conservation Code, would start using these technologies as the requirement for the design of the buildings. Here is another example of a test that it is being done. This is an experiment, which is not a studies experiment. It is called flip-flop experiment, and physicists love these experiments because it automatically compensates for the environmental condition. You identify two buildings as closely as possible together that are identical in operation performance. And then you monitor the performance of it. This is the east building, west building. As an example, when the east building is using 300 megawatt per day, the west building is using 350 megawatt per day. So you continue developing a correlation like a blue correlation in here. Then you suddenly put a white roof on one of them. You would find out that correlation from this would go to this. So therefore, when the building is using 300 megawatt hour, previously west was using 350, now it's using 300. So that shows that everything else is equal. This building has demonstrated to be using less energy. And then after this experiment is being done, you put white coating on this one, the correlation goes back to this. This type of flip-flop experiments is very, very popular among the physicists because, again, it allows to, without any doubt, to understand what's going on. This is something that a lot of people would have a question, and it is actually a myth. They think, a lot of uneducated people, they think that if the cool roofs are good during the summer, then the hot roofs should be good during the winter. But let us think about what is the difference between summer and winter. When you are talking about winter, in most climates, it would mean no sun. So a dark roof and a white roof would perform the same when there is no sun. How do you see that? Take it during the night. Take two samples when there is no light. One of them is white, the other is black. Look at them at the pure dark. You would not see any difference because there is no sun. That is the situation that we, even though it is so observable, but we had to do a lot of analysis to show people that in 4 cold climates of Anchorage, Milwaukee, Montreal, Toronto, we compared the performance of a cool roof on an air conditioning building, and there is a net savings in all those cold climates. Then this even did not account for the impact that snow would accumulate on the roof. If snow would accumulate on the roof, it doesn't matter whether it's black or white underneath. They perform the same. So once you accounted for that, you would find out that the savings are even higher. So here is the first rule of thumb. Anywhere that, for most application, that air conditioning is needed during the summer, having a cool roof would save you money. There are exceptions, but those exceptions are very, very few. Now, I'm going to go a little bit faster just to make sure that I'm not boring you much. The impact on a particular building is very, very easy to demonstrate. You can put a sample, change its color, and with an infrared gun, immediately see the temperature difference. But looking at the air quality and the climate, which is happening at a much, much larger scale, it is very, very hard to design an experiment to do that. It is costly. Also, the environmental variables are so many that you would never find 2 similar conditions that you can compare before and after. For that, you develop some models that you can account for those, such as if you have a meteorological models, by changing the reflectivity of the surfaces, you increase the reflected radiation, you reduce the surface temperature, and then you reduce the ambient temperature. The same thing with vegetation. It would, through evaporative condition, would cool the air temperature. The vegetation would increase the surface roughness. Vegetation would absorb some of the air masses of the pollutants. Also, vegetation themselves would emit emissions. So when you put all of these things together, it's a highly complicated factor. So we have been doing research in this area for the last 40 years. And we started with, first of all, we are not climatologists. We use the models and apply them in our condition. But we are also smart enough, if the model is not sufficient to do what we want to do a slight modifications to them. So that has been the focus of our research within the last 40 years. The models that we started with was Colorado State University mesoscale model. Then we went to MM5, and then after about 10 years dwelling on MM5, we moved to WRF, World Research Forecasting Model. Now, most people around the world use these models. For photochemical models, we had quite a few models, but right now there are 2 state-of-the-art models used. Most people look at WRF Chem, but some people also use the model that the Caltech is using. Professor Seinfeld at Caltech has developed CIT, and he's the only user, but since he is an authority in this field, he uses his model and only his model to talk to the others. And if you are talking to an authority, you have to come in turn with that. That's the model. So the principles of these models are very simple. This is actually one of my favorite slides. As engineers, we do not deal with many principles. We only have something like 5 principles that we deal with them. We apply these principles basically to everything. One of those principles are conservation principles. So you have conservation of mass, conservation of the mass on the first one, conservation of energy, conservation of momentum, conservation of water mass. In here, you have conservation of energy on surface. So you would say that I have an infinite number of grids over a domain. I divide them into those regions and apply these conservation equations into a finite difference scheme to solve those. You understand what is a finite difference scheme or not? How many of you understand finite difference? 1, 2. Okay, so for you have problem. You should go on 3. So divide this group into 3 groups, and you tell them what is the finite difference. So then, when it comes to the air quality, the same principle applies. Remember that nothing in the world is either being produced or destroyed. They always go from one phase to the other. So you have the same thing for the conservation of each of the components, pollutant components, that whatever is the change in a domain plus whatever it is brought in through boundaries is equal what it is being diffused plus what is the source, what is the sink, and plus also what is the transformation from one to the other, which is called depositions. So you would put all of these things together. Now here is the point. Now you have to solve a series of 200 partial differential equations simultaneously. Stability of your solutions is a major issue. Typically, in order even with supercomputers to model 1 hour of an actual weather, you need to have at the minimum 30 minutes of simulation. So if you want to run a simulation for 1 year, it would take your supercomputers half a year to do that. Who can afford that? So the way that you would do this kind of simulation, you try to only simulate it for few days in a month, or few hot days, or few cold days in order to document your principles. And here is an example of such analysis that we have done for few days. We planted 11 million trees in Los Angeles basin, and we simulated the temperature reduction as much as 3.5 degrees Celsius, but on the average about 2 degrees Celsius throughout the entire Los Angeles. We did simulations on air quality. We find out that not only the temperature changes, but the air quality improves. And this is actually a very interesting thing. Note that in some areas, the air quality has worsened. These are the areas, either overseas or the mountain areas that nobody lives. So when you are not doing anything with the surfaces, all those pollutants that have not been able to react, they have an opportunity to react somewhere that nobody is there, which is okay. So understanding this concept and passing it to the air quality measures is important. Now here is also another thing. You always find out a lot of people in your research find to disprove you, which is okay. As an example, an article has shown up in Los Angeles by a study that's showing cool roofs actually worsen the air quality. Now, you have so many things to do, but there is no way that you can let this thing go. You have to prepare an anti-article, say that this person has said this, but this is wrong, this is wrong, this is wrong, this is wrong. How many of you have read 2 books? The Philosophy of Poverty. Any of you? Philosophy of Poverty. During the 19th century, there was this French leader that was trying to describe why poverty exists. So he wrote a book which took him about, based on his own quoting, 20 years to write. Then a book came in 3 months after that, and the title of the book was Poverty of Philosophy. Philosophy of Poverty, Poverty of Philosophy. Who has read that book? Do you know who wrote that book? Karl Marx. And he had analyzed every sentence that Proudhon has mentioned in Philosophy of Poverty and show that Mr. Proudhon or Professor Proudhon doesn't know anything. He doesn't know what he's saying. He's talking from two sides of his mouth based on what he wants to say. So, by the way, the sales of the Philosophy of the Poverty had been throughout his life in the order of about 50,000. The sales of the Poverty of Philosophy had been in the order of 50 million. So people always come with these things, and we have no choice as an environmentalist for the people who are trying to have an effect on the lives of 10 millions of people that are born and died every day to be silent. Now, in an urban climate model, I'm going to make these slides very fast. Here is what you would do. You have a building. These buildings make a community. These communities make a cities. This city is part of a region. Air quality or weather forecasting models deal with the domain in the order of 1,000 kilometers by 1,000 kilometers. Now, if you break down this domain of 1,000 kilometers by 1,000 kilometers to 1 kilometer by 1 kilometer, the number of cells to deal with is huge. So your computational effort would be very, very high. So the way that you would do this type of analysis, you do through nested simulations. So that the grids in the outer range in here are in the order of 50 kilometers. Then you bring in the grids at this layer of the order of about 1 to 2 kilometers. Then you have another subgrid in the order of 300 meters to 1 kilometer. Now, trying to understand how to model this and interact them in between, most of the people who have developed WRF has dealt with this. But we are interested in this. Therefore, we have to interact and improve those models as we go forward. So there are been ways that we have done that. There has been a slab model that allows for the surface interaction and the boundary layer interaction. There had been a one-dimensional single-layer model allowing some structures, and there had been a multi-dimensional model that allow the air recirculation and absorption of the radiation through the multiple reflection throughout the urban settings. So obviously, this model would not be able to predict the environmental condition as good as this model is. So bringing in the understanding in this different level is important, and we have had several PhDs that have developed models using this type of application. So all of these things said, there are two ways to understand and answer questions. Number one is to be a listener to find out what is the practical question that people are asking and provide a tool to answer that question. Number two is that this is what I have. I have a hammer. Everything that you show me is a nail. So I'm going to apply this hammer on every question that you have. this type of technology, this kind of approach, would not work well with the environment and the policymakers. You need to understand how to design a process to answer a specific questions. For instance, how increasing the albedo on vegetation would have an impact on the urban setting. How much energy is saved in buildings. Each of these would have a different set of simulation tools and analysis tools. So there is not one size fits all. Therefore, you have to be able to have a comprehensive understanding and apply it properly. And now, the tools that we have, as I told you, for simulation is WRF, looking at the grid sizes with the nesting, understanding how to integrate the canopy layer model or the urban area into this, and finally, how to account for the chemistry and air quality. WRF is a very, very sophisticated model, and we basically do little with the WRF model. We spend most of our time in understanding how to prepare input for those models and how to analyze output of those models. In order to know the input and output, you have to know the details of the model itself. So even though we are not applying it the way that a climatologist applies, but as a practitioner, we have to be as good. Now, the physical models that WRF is using is being developed by climatologists. These climatologists would develop things on a larger scale, such as formation of a cloud is based on empirical relationship at the scale of 50 kilometers. Now, if you have an urban setting at the scale of 300 meters, you change the reflectivity of one grid, but do not change the reflectivity of the next grid. If you apply this model, you would find out that on this block you have cloud, on this other block next to it you do not have. Does there such a thing in reality exist? The answer is no. So wise application of these models, and to know how to apply them and where to apply them in their nesting approach is very important. So here is some of the results that with a multi-layer model and a slab model, we have looked at the performance. This is Montreal Island, and this is the island of Ile-de-Sers that my wife and I lived for about 5 years there, or 6 years there. And when you apply a different layer of modeling, rather than having in this course radiation budget or heat flux budget, you have this detailed heat flux budget. This is a lot more close to reality. Then understanding how to account for the effect of the urban settings, which is the buildings and the rows and the height of the building. You have the three-dimensional and two-dimensional models that you have to account. And here is simulations that you would do for 3 representative days for each of the months, and then try to interpolate for them in order to understand the effect throughout the city. Now, here is the important thing. Here is application of the cool roofs and cool pavements. Note that the impact is clear in the months of May, June, July, and a little bit of August. The rest of the months, there is not any effect. That's what they expect, because there is not much sun to begin with. So cool roofs do not have a negative impact in the winter season. Now, the effect of increasing the albedo in terms of the reducing the ambient temperature, that also is being shown. We can analyze that to see how much comfort it is. And the effect on the air quality, there are 4 simulations in here. One is a simulation of the ozone concentration in the urban area. One is the simulation of ozone concentration in the rural area. One is the simulation of ozone concentration when you apply white roofs and light roof and white pavement in the urban area, but it only is being shown as a difference with respect to this. So if you add this difference to this, you would get that new curve. And finally, the same is for the rural area. This is the same analysis in terms of understanding the particulate matters. This is actually, for some of you who may be interested, particulate matters is one of the biggest issue of the health. And the human body is very, very sensitive to the size of these particulate matters. Any particulates that is larger than 10 micron, it's being filtered out by our nose system. So you would find out during the summer when you are cleaning your nose that a lot of dark material in that. That is what it is being filtered out. Any material below 1 micron would go through our system and come back. But materials between 1 and 10 micron, which is characterized by 2.5, they would not be filtered by nose, but deposited in our lung. Those are the major health issues. So you would find that start playing a lot of simulations, such as if I plant trees along this street, what would be the effect on the comfort of the pedestrian? If I increase the reflectivity of the roofs or pavements, what would be the effect? And such examples are being shown with this type of simulations. And this happens to be done in my own background. So this is simulation of the ambient air temperature with in original phase after trees are being planted. This is a human weighted mean radiation temperature, which is comfort before and after. As you see, you can start doing this level of analysis. And now I'm changing the gear in terms of the science to the last point, which is cool surfaces also cool the globe. I mentioned that if you have a cool roof, that directly reduces your roof temperature and reduces your air conditioning. Now, what happened to that radiation that it is being reflected from that surface, being at the roof, pavement, or a mirror somewhere, has nothing to do with the energy use of the building. So shortwave radiation of the sun, such as a clear day like this, when it comes to the earth, if it is being absorbed by the surface, it becomes heat or long wave radiation. When the long wave radiation is going to try to escape the Earth's globe, it would be faced with the CO2 greenhouse effect. And as a result of that, it would not be able to escape very easily. Therefore, it would warm up the globe. Shortwave radiation, the same way that it has come in, it would reflect the Earth's surface. So this is known as Geoengineering 101. And here is a budget of the energy of the sun that it is coming to the surface, about 340 watt, about 198 is reaching the Earth's surface, and about 30% reflected, 168 is being absorbed. So this is a shortwave balance and the long wave balance in here, and I would not dwell on it, but I would like to mention this. We did some simulations which attracted a lot of international attention, and by taking the Earth and increasing the reflectivity of it by a certain amount within plus or minus 20 degrees latitude or plus or minus 45 degrees latitude. And then after that, we find out how many square meters of the land is in between these two and normalize that for that. So we find out that the temperature of the Earth for increasing the reflectivity of 1 meter square by 0.01 would reduce by about 3.5 times 10 to the minus 15 Kelvin. Very, 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 very small amount. But remember that this is per meter square. Now, if you have billions of meter squares, they suddenly multiply by this and the number becomes appreciable. And even more interesting was that if you increase the reflectivity of the Earth by increasing the reflectivity of 1 meter squared by 0.01, that would reduce the air temperature by a certain amount. You can also reduce the atmospheric temperature by taking CO2 from the atmosphere. Then you say, for the same temperature difference, how much equivalency I get? So if you increase the reflectivity of a surface by 0.01 per meter square, that is equivalent to taking 7 kilograms of CO2 from atmosphere. So in your own house, if you have a dark roof and you increase its reflectivity from whatever it is by 0.4, that's 40 times more. 40 times 7, that's 280 kilograms of CO2 per meter square. If a typical house is 100 meters square, that's 30 tons of CO2 equivalent. So you start thinking about it. Your car puts about 4 tons of CO2 per year. If you change the color of your roof, your house, you would offset 7 years of emissions of your car. Think about it. It's very, very important. These are the things that we can do easily. So you must all know that in 2015, the Article 2 of the Paris Accord came to the resolution of trying to limit the increase in the temperature to 2 degrees Celsius or 1.5 degrees Celsius if it is possible. And of course, you all have heard that non-President Trump has pulled out of the Paris Accord without caring what is going on. So trying to design and develop programs at such a huge international level is not very simple. So one has to really start putting collective efforts together to see how we can do that. And obviously the cool roofs and cool pavements play a significant role. Now, the beauty of this technology is that it saves you energy. It improves your comfort. It improves your air quality. It puts money in your pocket at no incremental cost. So now the challenge in here is that if I cannot sell this thing as an environmentalist, something that plus, no negative, then how in the world can I bring in communists together to say that your industry should limit their emission by this amount versus this amount? How can I deal with a person like a Trump? So these are our responsibilities as the students of today and leaders of tomorrow. Of course, not each one of us have the feeling, responsibility, and the honor to get to that level, but believe it or not, every single one of us has that kind of internal emotions We all would like to live in a better environment. We always would like to pass through the better environment. If there is a ghetto versus a nicer neighborhood, we always try to go through the better neighborhood. That is part of us. We always try to improve ourselves. Why shall not to do it now? So we have been developing various levels of standards in different levels for the state level, international level, and technology level that I would be talking about a couple of them back and forth in here. Here is an example of the standard that we developed almost 2 years ago, is the following thing. Manufacturers come with this practical question, that I have developed this material, and I would think that it does have superior performance properties, but I do not know how it is going to operate in 3 years. How can I improve its performance in 3 years? I cannot also afford the time to putting this material in the field for 3 years and then find out what my stake is. So you work with the manufacturers and come up with a procedure that would take about 1 week or 3 days that would produce the same result as 3 years. Manufacturers call you as their hero because you are asking and answering a practical question that they have. So this is one particular standard that we have developed. And here is the beauty of science. This is the material when it is fresh. This one, the red, is the material that is being aged for 3 years. This is the performance of the material that is artificially aged, the green one, in 3 days. Science at work and application. Education is a part of all the demand that we need to do. We have to make sure that we provide the right information. The information has to be so simple that everybody would understand, and also would not dispute. Now again, I have to ask you a question. How many of you have read Animal Farm? Wonderful, thank you. The story of Animal Farm is this, that a group of animals in a barn are complaining about the farmer, that they do all the work, the farmer gets all the benefit. The donkey does not getting enough food, the chicken would not be able to grow enough children because all their eggs are stolen, the horse is doing all the work today, so they revolt and then throw out the farmer out. And during this level, they find out that they need to coordinate themselves. A sheep is among a group of animals that do not have a good understanding. So all the directives that were being produced by the pigs are not understood by the sheep. So the pig come with the issue of trying to teach the sheep that all the animals are good, but human beings are bad. Now, sheep cannot understand animal. So the pigs come with the idea that something simple that the sheep can understand. 2 legs bad, 4 legs good. So now the sheep can simply understand that what is good, what is bad, how to inform and communicate with the other. Unfortunately, when we are dealing with a society, we have to go with the lowest denomination of the knowledge. And our message has to be very, very simple. So in order to do that, we have a variety of structures and organizations that we have started, such as Cool Roof Rating Council, European Cool Roof Rating Council, and the Cool Roof Rating Council in other countries, Global Cool Cities Alliance, and publicly run programs such as 1 degree less. Why such things are important? I am a customer, a manufacturer comes in and says that my product has a reflectivity of 90%. How in the world can I understand it? I do not have the tool. I need to have an organization to certify that this information is correct. So Cool Roof Rating Council measures, rates the performance of the material. So the customers, policymakers can easily apply it. The same thing, so this is the type of logo that they have. This initial solar reflectance is X amount. The initial thermal emittance is Y amount. European Council is doing the same thing with a 10-year delay. And there are always some issues of how to bring in the manufacturers into this game that is specific to the locations, and the local leaders must understand that. The Global Cool Cities Alliance, that another organization I started in 2010, is working on the simple idea of how to make the cities cool. Cool roofs and cool pavements. It would go and offer its services for free and help cities and mayors to develop programs. Remember that cities are responsible for 85 to 90% of all the energy used in the world. At this time, over 55% of the people of the world are living in urban area. By 2015, that number increases to 75%. So the local communities, mayors, city council have a lot of authority to make things happen. Guidebooks. Guidebooks are developed all around the world. The first one was developed by my group almost 30 years ago. Then other nations, such as the guidebook in Japan, has produced the information, minimal level of performance about the reflectivity of the roofs and pavements and the vegetation. Another institution in Japan also dealing with that. The similar guidelines are being produced for Europe with the leadership of La Rochelle University about 2 years ago. And the idea is to make sure that this technology is being used more often. So the bottom line is this. If you want comfort in the cities, the programs that you have to work is that. How to make the level of the heat emission in the city lower. How to improve the surface coverage in the urban environment. That would be both walls and the roofs, particularly if you're talking about the dense urban environment. Improving the urban form. In some cities that are being fastly developed, such as in China, it is easy to design the form of the city or the neighborhood from the get-go. But a practice like that in Italy is impossible because you already have established everything. However, Italy of 50 years from now would be different from the Italy of today. If that is going to go haphazardly in the direction of inefficiency, you would pay for it. Now it is the time to get integrated and think about this is where we are, this is where we want to go, and this is the roadway. And issues like that would apply. Now let me conclude with this slide. This is a repetition of a slide that I gave in Venice in 2014. And at that time, the new article came in, shows that the ozone hole in the South Pole is starting to repair itself. You all know that chloroforms have the negative ability of destructing ozone. Ozone is a layer that it is protecting majority of the Earth's surface from extreme UV light. Therefore, with the use of CFC, the ozone hole in the South Pole was increasing in size. In 1982, the Montreal Protocol, it is a non-committed protocol, but led by many nations throughout the world. They decided not to use CFCs in their processes. CFCs are mostly used in air conditioning and also in industrial processes such as manufacture of insulation. So they replaced CFC within a period of about 10 years to something new. Now, new data had shown since then the ozone hole in the South Pole has started to repair itself. It's shrinking in size. Good science, good policy, good results. Cool roofs save energy, save money, improves comfort, cools the world. Where is the cool policy, good policy? There are some in some part of the world, but not the others. Good results? Yes, we would get it. So we have to mobilize ourselves in that direction. So just remember this. If you change the reflectivity of a roof from a dark roof to an aged white roof, that is equivalent to offsetting 30 tons of CO2 for every 100 meters square of the area. If every city does that, that is equivalent to offsetting all the cars' emissions for the next 50 years. It doesn't solve the problem of global warming, but it is one of the components that has no cost. It is efficient, saves you money, that you should do immediately. It is a no-regret measure. With that, I conclude my comments. I show no hand during my presentation. I saw no hand. That would either mean that I have said everything so crystal clear that every one of you understood, or none of you cared. I'd rather to believe the first one. With that, I would be happy to answer any question if there is. Thank you. Oh, that's all right.
Grazie a tutti per essere intervenuti. Il professor Cotana non ha più voce, quindi io sono qui semplicemente per dirvi che se avete delle domande, avete un po' la barriera della lingua, semplicemente scriveteci e noi possiamo riportarle al professore che sarà qui per qualche giorno insieme a noi. Domani andremo a Roma in una conferenza organizzata dal CNR proprio dal titolo Albedo for Africa, e se avete delle domande adesso potete farmele in italiano e in inglese e eventualmente traduco. Curiosità o altro. Very shy because I asked them, okay, did you study design a difference? No. Yes, for sure.
There's no question.
Okay, Professor Corana, he has a question.
There is this question is the following, that there is an international measure called CRM that allows people to trade the right of CO2 emission. For instance, they come to a factory and then they tell this factory that your current emission is 100 tons per year. You can, if you reduce your emission, you can sell the additional right to emit by certain amount, such as 20 euros per ton. So as a factory, I have an option to find a way to improve my efficiency so I would have less CO2 emitted, therefore I would be able to sell it. When I sell it, I get more money. Now, that free market has not, of the CO2 trade, has not performed well within the last 20 years. The reason for that is people have not been able to complete the cycle of production that not only deals with the production, but also deals with the waste management. CO2 is a waste of combustion, but we can emit it very easily everywhere. Therefore, as long as there is not a strong regulation, the cost of the CO2 emissions are very low. And one of the factors that COP21 was going to deal was to create that market in a realistic price. Right now, the CO2 value is about 20 to 30 euros per ton. In terms of the kilowatt hours, that would be in the order of about half a cent per kilowatt hour increase in our energy costs. So, is that the way it's supposed to be? The answer is no. If we look at the consequences of the global warming, how much hazard it would create, and how to pay for those hazards, that's one. Or to start devising ways not to create those hazards. As an example, the recent 2 storms, category hurricane in the United States, has cost United States over $100 billion. Now, that $100 billion, of course not all of that, could have been, half of that could have been avoided by reducing the emissions. Now, you take that, you find out how to reduce emission, divide them together, you get the realistic cost of CO2. In my humble opinion, if we try to reduce the emissions in the world by the year 2100 to 0, then the cost of CO2 emission should be in the order of $3,000 a ton. But try to make sense into people like Trump in that respect.